In this video, we're going to be talking about topic 7.2, frequency and period of simple harmonic motion. So let's start off with deriving some of the equations that you're going to use. So we have angular frequency, and this is going to be this formula here. Omega is equal to the root of k over m. So we're going to start off with Hooke's law. We have F is equal to negative k of x. And then applying Newton's second law, F is equal to ma. We can write ma is equal to negative k of x. And from this, we can rewrite to solve for acceleration. So we have acceleration d squared of x over of t squared. Thus, we have m d squared dt squared negative k of x. Now, rearranging this to everything onto one side, we have squared x over dt plus k over m, x is equal to 0. And this is and we can also substitute k over m. So we have d squared x dt squared plus omega squared x is equal to 0. So now we have omega squared k over m. So from this, root both sides, we have k over m. This is the standard simple harmonic motion differential equation. And this is the derivation. Now we can derive the period. So to start off with this derivation, we have the definition of angular frequency, which is omega is equal to 2 pi over t. Solving for t, we have 2 pi over omega. And we can substitute in omega is equal to the root of k over m. Substituting this in, we have omega right there. And then we can rewrite this as t divided by 2 pi over the root of k over m. And we can rearrange this so that we have t is equal to 2 pi over the root of m over k, simply by swapping that, taking the reciprocal of that, so we can move it up to the numerator. Now, if we want to derive frequency, we can start off with the definition of frequency, which is F is equal to 1 over t, and we can substitute in the expression for t. So we have F is equal to 1 over 2 pi times the root of m over k. And if we want to bring that up to the numerator, we can just take the reciprocal of the root of m over k. So we have root of k over m, and that is our frequency. Now for our acceleration, we can start again from Newton's second law, which is ma is equal to negative k of x. Now solving for acceleration, we have a is equal to negative k over m times x, and we can substitute in omega squared is equal to k over m. Right there. So then we're left with the acceleration is equal to negative omega squared times x. So we can see that acceleration is proportional to the displacement. And we can also see that the acceleration points to equilibrium, and also the acceleration depends on the position, not velocity, as it did before, which was previously we saw that we know acceleration is the change of velocity over the change of time. And now we have, for period and frequency, we can look at here, we can see they only depend on mass. This only depends on mass and also on spring constant K. So this is independent of amplitude. And also, we know that frequency is independent of amplitude because it doesn't involve amplitude. It only involves M and K here. A block of mass M oscillates on a horizontal spring with spring constant K and period T. A second block of mass 3M is attached to the same spring. Find the new period in terms of T. Determine the ratio of the new frequency to the old frequency. For a mass spring system, T is going to equal to 2 pi root of M over K. Our new mass is going to equal to 3M. So we have T2 is going to be 2 pi 3M over K. And that will be root 3 over T. The formula for frequency is 1 over T. So we have the ratio of F2 over F1. That's going to be T over T1, and that's going to be 1 over root 3. Or the new frequency to the original frequency. So that's actually going to be, yes, T2, and this is actually going to be T2 and T1 because this is flipped. A mass M oscillates on a vertical spring with period T. The system is rotated so the spring is horizontal, keeping the same mass and spring. Find the new period. T is equal to 2 pi root of M over K. The period for a spring, it only depends on M and K. So gravity will shift the equilibrium position only. It does not affect oscillations because gravity is not accounted for in formula for period. It is independent, so it would be the same. Two simple pendulums have lengths L1 and L2 are equal to 4L1. Find the ratio of their periods. T is equal to 2 pi times L over G for the period of a pendulum. So we want the period ratio. And that is going to be T2 over T1, which is equal to L2 over L1. That's going to equal to the root of 4, and that's going to equal to 2. Frequency is the inverse of period. F is equal to 1 over T. F2 over F1 is equal to T1 over T2, which is 1/2. A 80 kilogram block oscillates on a horizontal spring. It completes 12 oscillations in 15 seconds. Find the spring constant K. So the frequency is going to be equal to 12 over 15. And that's going to be 0.80 hertz. Now we want to find the angular frequency, which is going to be omega is equal to 2 pi times f. That's going to be 2 pi times 0.80, and that's going to be 1.6 pi. Now, using omega is equal to the root of k over m, by solving for k, we can square both sides. We're left with omega squared k over m, multiplying both sides by m. We're left with k is equal to m times omega squared. Plugging in our values, we have k is equal to 0.80 times 1.6 pi squared, and k will approximately be 20.2 newtons per meter. A simple pendulum has a period of 1.2 seconds on Earth. The same pendulum is taken to a planet where the gravitational acceleration is 4.9 meters per second squared. Find the new period. The period of a pendulum is t is equal to 2 pi root L over g. Now the ratio is going to be t2 over t1, and that is going to be the gravity of the Earth divided by the gravity of the planet. We can compare that because we have 4.9 and we also know Earth's. 1.20 times 9.8. Oh, for just T1, for T2, I mean, we have 1.20, 9.8 over 4.9, 1.20 root 2. Therefore, that's approximately 1.7 seconds. Two identical springs of constant K are connected in series and attached to a mass m. Find the period of the oscillation. So, the effective spring constant for springs in a series is 1 over k effective is equal to 1 over k plus 1 over k is equal to 2 over k. Therefore, we have this. So now we can flip the whole thing. K effective is going to equal to k over 2. Now to find the period, that is equal to 2 pi times the root of m over k effective. Therefore, t is going to equal to 2 pi times the root of 2m divided by k. That's going to be root 2 times 2 pi root m over k. And t is going to equal to the root of 2 times t single. A mass on a spring has an acceleration given by a is equal to negative 16x, where x is in meters and a is in meters per second squared. Find the angular frequency. The angular frequency in simple harmonic motion form is a is equal to negative omega squared times x. So, therefore, omega squared is going to equal to 16, and taking the root of both sides, omega is just equal to 4 radians per second. Now, in order to find the period, t is equal to 2 pi over omega. Here, we have the omega we just found is 4. So t will equal to pi over 2, which is approximately 1.57 seconds. A student doubles the amplitude of oscillation of a mass spring system while keeping all other variables constant. Which quantities change and which stay the same? Period will be unchanged. Frequency will be unchanged. The maximum speed, which is Vmax, is equal to omega A. That will increase. The total energy, E, is equal to 1/2 Ka squared, amplitude squared. That will also increase. A mass spring system has a period T1 is equal to 0.8 seconds when a mass M1 is equal to 0.5 kilograms is attached. When an unknown mass M2 is attached instead, the period becomes T2 is equal to 1.2 seconds. Find M2. So for a spring, the period is equal to 2 pi times the root of m over k. If you take the ratio of this, you have T2 over T1 is equal to the root of M2 over M1. Now, if you square both sides, you have 1.20 divided by 0.80 squared. Using the values that we have here, that is going to equal to M2 over 0.50. Simplifying this, we have 1.5 squared is equal to M2 over 0.50, and we have 2.25 is equal to M2 over 0.50. So we have that M2 is equal to 1.125 kilograms. A pendulum's angular displacement versus time graph shows that the pendulum completes 5 full oscillations in 12.5 seconds. Find the period. The period is equal to t, and that is 12.5 over 5, and that is equal to 2.5 seconds. The formula for that was t is equal to 12.5, which was seconds over the oscillations. The frequency is equal to 1 over the period, so that is going to be 1 over 2.5 seconds. That is going to be 0.40 hertz. And the angular frequency is omega, which is equal to 2 pi times the frequency. 2 pi times the frequency we found of 0.40. That is approximately 2.51 radians per second. A simple pendulum has a frequency of 0.5 hertz. Find the length of the pendulum. The formula for frequency is F is equal to 1 over 2 pi times the root of G over L. Now solving for L, what we can do is we can multiply both sides by 2 pi. Now what we can do is we can square both sides. And after this, that will cancel out the root. And then we can divide by 1 over g. So then you're left with L is equal to G over 2 pi F squared. So now if we plug in our values, we have L is equal to 9.8 divided by 2 pi times 0.50 squared. And that's going to be equal to 9.8 times pi squared, which is approximately equal to 0.99 meters. Spring A has constant K. Spring B has constant 4K. The same mass oscillates on both strings. Find the ratio of the periods TA to TB. So from the period formula, we know that T will be proportional to the root of 1 over K. So when we take the ratio of TA over TB, we have KB over KA, and that's going to be equal to the root of 4K over K. The square root of 4 is 2, and the K's cancel out, so you're left with 2. So that's going to be a 2-to-1 ratio. A particle moves such that the force is F is equal to negative 25x, where F is in newtons and x is in meters. The mass of the particle is 0.4 kilograms. Show that the motion is simple harmonic motion. Well, we have ma is equal to negative 25x using Newton's second law. F is equal to ma. So from here, if we solve for the acceleration, we have negative 25 over 0.40 x, and we have the acceleration is equal to negative 62.5 x, and we can compare this with the a that we can calculate a separate way, which is a is equal to negative omega squared x, and from here we can divide by negative x. So we can have omega is equal to, omega squared is equal to 62.5. So the motion is simple harmonic motion. Now to find the angular frequency, omega is equal to the root of so that's going to be 7.91 radians per second. Now for the period is equal to 2 pi over omega. T is equal to 2 pi over 7.91 rad per second. T will be equal to 0.79 seconds. A spring of constant K has mass m attached and oscillates with period T. Another identical mass is gently attached, so the total mass is 2m. Find the new period. So the period is equal to 2 pi times the root of m over k. The new period is equal to 2 pi times the root of 2m over k, which simplifies to the root of 2 times t. A pendulum has length L. The elevator accelerates upward with an acceleration a. Find the new period of the pendulum. So the effective gravity is going to be equal to the gravitational constant plus a. The new period is equal to t, and that's going to be 2 pi times the root of L g plus a. So the period decreases compared to rest. That's because the denominator increased. So total value decreases. A mass spring system has its amplitude tripled. Which of the following change? So, period, frequency, and angular velocity, these all only depend on m and k. However, energy is equal to 1/2 of Ka squared. So, if you triple the amplitude, then you have E is equal to 1/2 1 times 3, and that's squared. So that means it will increase by a factor of 9.